Consider the following two scenarios. A data source, such as an analog-to-digital converter, writes data into your DDR memory. The system then needs to transfer the buffered data to the host machine for visualization or further processing. You have data, like an image, stored on your host machine's hard disk or DDR memory, and you want to transmit it to your embedded board. Which protocol would you use? Would you opt for UART, or would you prefer Gigabit Ethernet with the TCP protocol? The Zynq UltraScale MPSoC features a powerful Gigabit Ethernet implementation within its processing system, offering up to 4 integrated Gigabit Ethernet MAC controllers. Part of the controller's configuration is performed in the Vivado IDE based on the datasheet of the selected evaluation board or the available board files. The PS-side Gigabit Ethernet MAC implements a 10 and 100 and 1000 megabits per second Ethernet. Interface of these controllers supports flexible connectivity options through RGEM and GMII interfaces for external PHY connections, allowing seamless integration with various network architectures. One of the most significant advantages of this implementation is its sophisticated DMA engine with scatter-gather support, which efficiently handles data transfers while minimizing CPU overhead. Two groups of pins are connected from MAC controller to the PHY chipset. The first one is MIO pins that covers the various transmit and receive lines needed for Ethernet communication. The MDIO pins facilitate communication between the MAC controller and the PHY chipset, enabling configuration, status monitoring, and management of the PHY. Vivado design. In Vivado, you need to include the Zynq IP. If you are working with Xilinx AMD evaluating boards, run block automation. This process configures the IP with preset parameters that match to your evaluation board layout. The DDR4 memory controller is set up for the onboard 4 GB DDR4 memory. Please note that to run the Echo Server, a proper DDR connection is essential to provide the application with sufficient memory space. Now, let's have a look at Gigabit Ethernet MAC. The preset selects MIO 64 to 75 for Gem 3, corresponding to the schematic and image. This covers the various transmit and receive lines needed for Ethernet communication. It also setups the MDIO pins as the communication link between MAC controller and PHY chipset. There are two important points to note. There are two different setups, RGEM and SGEM. If MIO pins are selected in the setup, it means you have an RGEM setup. Typically, evaluation boards come with an RGEM setup, and this video focuses on RGEM Ethernet. If the Giga line transmitter is selected, then it corresponds to an SGEM setup. Since master ports are not required, navigate to the PSBL interface and deselect the two master port interfaces. Alright, we are done in Vivado. We need to add top HDL wrapper and generate the bitstream. After bitstream generated, we need to export the XSA and include the bitstream in the exported XSA as well. Before creating the Vitis project, it's a good idea to have a look at the different protocols that involved in Echo Server template. Transmission Control Protocol is a fundamental networking protocol. It ensures reliable, ordered, and error-checked delivery of data between applications running on hosts, communicating via an IP network. Lightweight IP is a widely adopted, open-source TCP IP stack designed specifically for embedded systems with limited resources. It provides a robust networking implementation while maintaining a small memory footprint, typically requiring only tens of kilobytes of RAM and around 40 kilobytes of ROM. LWIP achieves this efficiency by carefully implementing only the essential features of various networking protocols, including TCP and UDP, while allowing developers to configure and scale the stack based on their specific requirements. The Vitis IDE from Xilinx provides developers with a LWIP TCP Echo Server template example. It serves as an excellent starting point for embedded networking applications. The TCP Echo Server implements a simple server that listens for incoming TCP connections on a specified port. When a client connects and sends data, the server simply echoes back the received data. Vitis design. We need to create a new project with the exported hardware from Vivado. Follow the normal routine, and you can select any of the listed ARM cores. For operating system, select FreeRTOS. On FreeRTOS is much easier to understand the Echo Server example since it allows multi-thread applications. From the provided list, select Echo Server Template Example. The Echo Server example is a really big project, but I'll show you how you can build your application on top of that. Board Support Packages. Let's take a look at the board support packages. For Ethernet connection, you have two options. Using an Ethernet switch, connect both the board and your PC to an Ethernet switch. In this setup, the DHCP protocol will assign an IP address to your board automatically. Direct connection. Connect your board directly to your PC. In this case, the evaluation board will use a default IP address, and you will need to manually assign a static IP address to your PC. PHY speed setup. You can select the PHY speed from a drop-down list, or allow it to be determined automatically through auto-negotiation between the FPGA and the PHY. Congratulations! You're all set to run the Echo Server example. Build your project and prepare to connect your board directly to your PC. Once connected, launch the application on the evaluation board. You should see a success message on the serial terminal displaying the IP address and port number of the server. Now, open the CMD window and validate the Echo Server by using a simple ping command. Echo Server Template Overview. The first important file is the main file, which contains a section where you can configure the IP address, netmask, and gateway settings. This section of the code creates a new thread named Echoed. This thread runs the Echo application thread function, which is defined in the Echo C file. This code initializes and starts the Echo server in its own thread, and then cleans up the current task to free resources. Echo C file. The file you should focus on the most is the Echo C file. The process Echo request function handles an individual client connection in the Echo server. It reads incoming data and echoes it back. Main loop. The loop continuously processes data from the client until a termination condition is met. Reading data. This reads up to 2,800 bytes of data from the socket into the defined RX buffer. Echoing data. The function writes the received data buffer back to the client. This is the core behavior of an Echo server. The default Echo C file only defines one buffer as RX and TX buffer, which limit our functionality. I have created two projects with a modified Echo C and a Python script for correct data transfer between the PC and evaluation board. For each project, you need to download these files, replace the Echo file, and run the Python script in your host machine. The first project continuously reads data sent by the client, appends a predefined suffix to the received message, and sends the modified message back to the client. The Python script sends a message to the server and prints both sent and received message. Let's run the first project and observe the results. You will see that the client first connects to the server, sends a message "Hello World" to the server, and then receives a response from the server with the appended suffix. In the second project, the Python script sends a sine wave signal to the server. The server receives the signal, and the ARM core performs two signal processing operations on it, calculating the absolute value of the signal and multiplying it by a constant. The process signal is then sent back to the client. Finally, the Python script receives the process signal and displays both the sent and the processed received signals. Let's test and validate the second project. You should see a sine wave as the transmitted signal and its absolute value as the received signal.